Hello everyone, my name is Nihar Shah. I am from MTech Series Coursework and today I am going to talk about quantum computing. Before delving into quantum computing, I would like to take a step back and talk about the prerequisites or the background required for quantum computing. So, if you're interested in quantum computing, it's important to have a good understanding of linear algebra. Now, why is it so? Because linear algebra is the framework of quantum computing. So, every concept, everything you learn in quantum computing has somewhere its roots in linear algebra. If you're interested in understanding quantum algorithms, it's preferred to have knowledge in linear. It's required to have a knowledge in linear algebra, as well as it's preferred to have a knowledge in quantum complexity theory, because in order to understand and analyze the quantum algorithms, to know the complexity classes and all, it's better to have a knowledge of quantum complexity theory. Now, the requirement for quantum complexity theory prerequisite is classical complexity theory. So, if you are interested in quantum information theory or quantum error correction, it's important to have understanding of classical information theory. It's preferred to have knowledge of classical information theory and classical error corrections. Okay. So now we'll move on to the as aspects of quantum computing. So in this video, I'll talk about principles of quantum computing. I'll talk about some famous algorithms, some uh, challenges and caveats of quantum computing, as well as the advantages of quantum computing, and so on and so forth. So we'll start with principle of quantum computing. Now, in case of a classical computer or classical bit, you must have heard of a classical bit being in state either 0 or in state 1. The quantum equivalent or quantum bit could be in state 0 or 1 or a superposition state. Now, what do I mean by that? So let us understand what does a qubit mean. So consider I have a qubit. Now, as I said, qubit can be either in state 0, 1 or in some superposition state. Now, in case of a classical bit, we represent the classical bit by a scalar, right? 0 or 1. A classical bit can be represented by a scalar 0 or 1. But that's not the same case for a quantum computing or a quantum bit. In case of a quantum bit, qubit, the representation of a qubit is done by a vector, which is in two-dimensional complex vector space. Now, what do I mean by two-dimensional complex vector space? So, over here refers to the coefficients or the alpha, or the coefficients of the vectors or the entries in the vector are complex. So so the qubit exists in a two-dimensional complex vector space. Now, what do I mean by by state 0, state 1, or in a superposition state? So the state 0 or ket 0, it said this is the representation of a ket or a vector in quantum computing, and it's represented by the state 0 is represented by a ket 0, a vector which is this vector 1 0. 1 in the 0th position and 0 in the 1th position. Similarly, ket 1 is the equivalent representation of state 1, which is represented as 0 1. That is 0 in the in the 0th position and 1 in the 1th position. So basically, any ket I can be represented as zeros, all zeros, and 1 in the ith location and 0 everywhere else. That's the representation of a ith ket or ket ith vector. That's what it means. Now, so when I say qubit in state 0, that is qubit is in this, the qubit is represented by this vector. When I say qubit is in state 1, it means that the qubit is represented by ket 1, this vector. Now, when I say qubit is in state in a superposition state, I mean that the qubit is represented by this vector, which is where alpha beta belong to are complex numbers, and this is equivalent to saying this vector. So it's a linear combination. If you know linear algebra, it's a linear combination of ket 0 and ket 1. So, and ket 0, ket 1 could be thought of as canonical basis states. So as I said, qubit exists in two-dimensional complex vector space, and this two-dimensional complex vector space has ket 0 and ket 1 as their classical basis states or classical states, similar to a classical bits or classical computing case. Ket 0 and ket 1 are the classical basis states, and when I say that the qubit exists in superposition, it means that it exists in this two-dimensional complex vector space formed by the basis states as a linear combination of those two states. So it's alpha ket 0 plus beta ket 1. And this is equivalent to saying alpha, this vector alpha beta, where alpha beta are complex numbers. So it's a qubit, and this is superposition state of a qubit. So when I say the qubit exists in a superposition state, it means that it exists in a complex dimensional vector space, two-dimensional complex vector space. So the entries of the vectors are a complex number, and the basis states are formed by 0 vector and ket 1 vector, and this is what 0 and 1 vector are. So it's the same as canonical basis. So this is what a superposition state means. So now, In case of a classical computing, if I take 2 bits, it's the states possible are 0 0 0 1 1 0 1 1. So if I take a classical bit, if I take two classical bits, then the states possible are 0 0 0 1 1 0 1 1. But what if I take two qubits? What if I take two qubits? What are the states possible, or what is the how do I express the equivalent of two qubits for a two, like equivalent of two classical bits in qubit sense, in two qubits, for two qubits. So two qubits can be represented as follows. So consider, let me represent it, one qubit as alpha cat 0 plus beta cat 1, which will be in some state alpha cat 0 plus beta cat 1. Let me represent the second state by phi as say theta cat 0 plus gamma cat 1, something like this. Now what if I take these two qubits together? So how do I represent these two qubits? In some ways there is some notation. So the principle says over here, says that how do you represent multi-qubit state. So multi-qubit state, or over here in this case two qubits, is represented as a tensor product of those two states. So it's a it's a tensor product. So how do I, so it's a tensor product means this. So if I write it as the standard notation form, it will be theta gamma, and so I can write this as alpha theta alpha gamma beta theta beta gamma. And this is a complex four-dimensional complex. This exists in a four-dimensional complex vector space. So let's just recap. So like in classical computing, the two classical bits are represented as 0 0 0 1 1 0 1 1. In case of quantum computing, the two qubits are basically represented as the tensor product of those two qubits. So when I say I have two qubits, it exists in 2 to the power 2 dimensional complex vector space. Suppose I have n qubits, then it will exist in 2 to the power n dimensional complex vector space. And as I said earlier, that the complex two-dimensional complex vector space. So complex vector space means the entries of the vectors could be complex numbers. So that's what over here is happening. So let us let us move back to the statement. So state space of a multi-qubit system is tensor product of the state space of the individual qubit systems. So state space, or as I said in the previous case, that the state space of first qubit was two-dimensional complex vector space, and the state space of second vector was another two-dimensional complex vector space. So state space of this multi-qubit system, when I combine those two qubits together, is basically a tensor product. So you take tensor product of these two state spaces, so complex vector 2 times tensor product of complex vector 2, which will give me complex vector of a four-dimensional complex vector space. Similarly, if it's n, for n such vector spaces, suppose there are n such vector spaces, it will be C power 2 power n dimensional complex vector space. Hope it's clear. So okay, so now we understand what's superposition. Now we understand what's a multi-qubit state space, or a multi-qubit, how to represent state space of a multi-qubit system. It's basically tensor product of the individual qubit systems, right? That's what we did. So now we understand this part. Now, so what is simultaneous? So how is it helpful? I mean, how is it helpful, or how is it better than the classical computing, or is it better? Can we even use it or not? So the idea behind this is that a superposition state allows simultaneous computing. That is, suppose I want to, if I ask you that what is, suppose I have a function such that it takes an input and gives you output. Suppose it takes 0 in as classical bit as input, 0 as input, and gives the corresponding answer. And if it takes f of 1, that is 1 as input, and gives some answer. So this is what happens in case of classical computing. Suppose I ask that what is the answer for the, or to evaluate the functions on input 0 and 1. So what you'll do, you will input 0 to the function, you'll get the answer. You'll get input 1 to the function, you'll get the answer. So it's two steps, or two computing. So the number of computations done is 2, right? You need to evaluate the function on 0, and then you need to evaluate the function on 1. So you were required to do two function evaluations, or two computing steps were required to be done in order to get the answer. But same thing in case of a quantum computing. If I create a superposition state such as this, and I input this to the function, then it will give me output, which is also a superposition state of the which is the result of f of cat 0 plus f of cat 1. Now over here I'm skipping a lot of physics behind it, or lot of math and lot of things behind it, but roughly this is true. I mean, roughly this is the idea behind it. So if you, so this is only one function evaluation, right? So this is what the superposition state allows us. That is, superposition state allows us to do a simultaneous computing step. Now, will it be advantageous or not? Can I use it or not? So that's a lot of lot of caveats over there, which will later on involve in this video. So this is basic idea behind what quantum computing does, right? So in case of classical computing, it required two function evaluations. Okay, note that over here I'm not considering parallel computing or something in distributed computing setting. I'm considering a serial computing setting. That is, I have only one laptop, one PC, and I can only evaluate I can only do computation in serial. Only serial computations are allowed. So if I want to evaluate the function on 0 and 1, I need to find f of 0, then I need to find f of 1. So it requires two function evaluations, or two computation steps are required. But in the quantum computing setting, using a quantum bit in a superposition state, I can create the superposition state such that it's in 0 plus 1 state. Now, and if I input this state to the function, then the output of the function is another superposition state, which has the results of f of 0 and as well as f of 1. So it just required only one function evaluation. So roughly, and this is not the exact idea behind, this is not what gives advantages to quantum computing and so on and so forth, but this is roughly the idea behind allows a superposition state. Superposition state allows us to do parallel simultaneous computing. Now, will it be advantageous? Can I use this as an advantage or not? We'll later on see what's actually, whether it's better or not. So then we'll move on to the fundamental entanglement. Now this is one of the other aspects of quantum computing, quantum mechanics, which allows us to have certain advantages. Now in case of a classical bit, all the bits are independent of one another, right? You cannot have operation on one bit does not affect in any way the operation on the other bit. This is true, although this is true in case of classical computing, but it's not true in case of a quantum computing. If your states are entangled, that is, if you are two qubits and two qubits are entangled in some way, and then the entanglement somehow, if I do operation on one qubit, will affect the results of the second qubit as well, and that's a simultaneous. It's an instantaneous operation. So operation on one qubit also somehow affects the operations or affects the state of the second qubit. That's what happens in case of a quantum computing setting, but which is not true in classical computing, right? In classical computing, the bits are independent, so operation in one bit does not in no way affect the operations on other bits. But this is not true in case of quantum computing. Quantum computing, if the states are entangled, the states should be entangled. Now, if the states are entangled, then operation on one qubit will affect, or may affect, or might affect the state of the second qubit. Now, how could the entanglement be advantageous? Well, it could be advantageous in certain cases where we want to perform certain operations quicker, or certain operations we want to perform which also affect the state of the second qubit. So we can just perform one operation and will also affect the state of the second qubit or other qubits. Unitary evaluation. Now, one of the main aspects or one of the main requirements of quantum computing is that the state evaluation, that is given a qubit, if you want to change the qubit state. Suppose I want to change my qubit state from cat 0 to cat 1. Suppose I have a qubit and I want to change the state of the qubit from cat 0 to cat 1. So how do I do that? I have a qubit. I want to change the state from cat 0 to cat 1. So how do I do it? So I need to perform some operation, right? That's what I need. Now, what's this operation? Now, this operation must be unitary. That's a requirement. That's an axiom, kind of like a requirement of quantum computing. You cannot perform non-unitary operations on a qubit, or on a classical computing system, on a quantum system. So this is called as evaluation, unitary evaluation axiom. So the thing is that if you have a qubit, if you have a state of a qubit, and if you want to change the state of qubit somehow to some other state, then the operation must be unitary. That is, what do I mean by unitary operations? So I need a unitary matrix, a unitary operator, U, acting on the state of the qubit in order to get some other state of the qubit. This U must be unitary. And if you recall from linear algebra, unitary operations or unitary matrices are simply this matrices which follow, which satisfy this So yeah, that's all about unitary evaluation. So okay, now we'll move on to the second. That's the measurement. Okay, so let us understand. Okay, before going to before understanding the measurement, let us take an example in order to understand what's actually happening over here. I mean, how is this different from a classical perspective and quantum perspective? So yeah. So consider a coin analogy. I always like to think of this as a coin analogy in terms of coin. So consider you have a coin. Now this coin can either be in state heads or tails, right? So it can be either in heads or it can be in tails. Now, uh, suppose I have a coin which is initially in state heads. Now there are two operations I can perform on this coin. I can either toss a coin or I can either measure the coin. Now what do I measure? Measuring the coin. Now over here measuring just means that I can look at the coin. The coin, seeing the side facing upwards. Facing upwards. This is what I can do, right? So when I say I measure the coin, what I mean is I'm looking at the side that is facing upwards. So now what we can do with the coin? So suppose I have a coin which is currently the side facing upwards is heads. I can either toss that coin or I can either measure that coin. Note that tossing the coin, I don't look what the side is facing upwards. When I toss the coin, I don't know what the side is facing upwards is. But if I measure the coin, I can know the side facing upwards. Suppose I have a coin which is facing upwards heads, and I toss that coin. Then the state of that coin would be with half probability heads and with half probability tails. Suppose it's an unbiased coin. I'm assuming that the coin is unbiased, and if I toss that coin, then the state of that coin will be half heads with probability 1 by 2 and tails with probability 1 by 2. That's a basic mathematics, basic probability from 10th standard, 10th grade. Now suppose, okay, this is clear, and then now suppose if I toss the coin again. So what's the outcome? And if I toss the coin again, it will again be half probability heads, half probability tails. That's the state of the coin. Now suppose I measure the coin now, and I found out that the state of the coin was tails. Tails was facing upwards. So then the state of the coin is one probability with probability 1 tails and 0 probability heads. Right? This is what is happening over here. So as I said, if we had an unbiased coin, we can either toss the coin or we can either measure the coin. If I toss the coin, it's probably heads with probability 1 by 2 and tails with probability 1 by 2. And if I toss the coin again, it will be still remain in the same state, half probability half with 1 by 2, 1 by probability heads with probability 1 by 2 and tails with probability 1 by 2. And if I measure the coin, I could either get tails or heads with probability 1 by 2. And suppose I'm on measuring the coin, I get tails as facing upwards, and then the state of the probability becomes one tails with probability 1 and 0, heads with probability 0, right? So let us make this more formal. I mean, this is what the general mathematical, I mean, let us make this more mathematically formal. So mathematically I can talk about it as follows. I can represent the state of the coin as a two-dimensional vector, where the first entry represents for heads, the probability of getting heads, and the second entry represents probability of getting tails. Initially, the coin was heads. If you recall, initially the coin was facing up. The heads was facing upwards. So the coin was in state 1-0. That is 1 with probability 1. So if I measure if the coin was missing, facing heads upwards, and if I instead of tossing the coin, if I measure the coin, I'll get heads with probability 1 and tails with probability 0, because I already know that heads was facing upwards. So currently this is the probability state. This is the state of the this is the probability state of the coin, right? Okay, that's good. Okay, so now let us understand what's the probability state of. I mean, what happens when we do a tossing? When we toss the coin. So this tossing operation can be represented by this matrix 1 by 2, 1 by 2, 1 by 2, 1 by 2. Okay, so let us multiply this matrix with the vector. So we are performing this operation on this vector. So what I get is 1 by 2, 1 by 2. And that's true. That is probability of getting heads is 1 by 2 and probability of getting tails is 1 by 2. That is true. If we toss the coin, the probability of getting heads was 1 by 2 and the probability of getting tails was 1 by 2. And this is what we get. This is what we are getting as the state of the coin right now. Suppose I make a measurement over here. Then upon measurement, the state was tails, if you recall. So the probability of getting, probability of getting tails was 1, probability of getting heads is now 0. So this is the state of the coin after measurement of tails. I measured the coin, I got tails as facing upwards. So this is the state of the coin then. So mathematically, we can make a framework such that we can represent the state of the coin as this probability vector 2 cross 1. Then we can either toss the coin or measure the coin. If I know the state of the coin 1 0, and if I measure the coin, it will remain in the same state, right? It will still be 1 0 heads and tails. Probability of getting heads at 1 and probability of getting tails at 0. So if it's already in heads and if I measure the coin, it will be in heads, and that's what we know. We know from the classical setting that it will be if I look if it's already heads. If I look at it again, see the face see the face that's see the coin and see what's facing upwards. It's heads, so that's probably 1 0. And this is the state that represents that. Suppose I toss a coin, then the tossing operation could be represented by matrix, this matrix, and this matrix represents the tossing operation. And upon tossing, the state of the matrix or the state of the coin will be this: half heads and half tails. Probability of getting tails is half, and probability of getting heads is 1 by 2. This is the state of coin after tossing the coin. But if I measure the coin, and suppose I find that the coin was facing, the facing upwards was tails was facing upwards. Tails was what we measure. Then the state of the coin becomes this. Now I hope you understand what's actually happening with the coin in classical setting. I can either toss the coin or I can either measure the coin. Tossing is represented by matrix in operation, and if I perform, this is just matrix vector multiplication, that operation, and if I perform this matrix vector multiplication, this is what I get, the new state of the coin. And if I do a measurement operation on this state, then it will be simply the 1 in the entry that I get and 0 in the other entry. So I hope it's clear what is actually happening. Now let us see the quantum equivalent of it. So let us see the quantum equivalent of it. Now what happens in case of quantum computing? Suppose I have these same kind of things. Let us see what happens in case of quantum computing. So same is what is we are seeing with quantum computing. I have a qubit. I can either perform some operation, or in the case of classical computing, it was, in the case of coin, it was tossing the coin, or I can either measure the qubit. In the case of coin, it was measuring, means looking the side facing upwards. Let us see. We'll understand what in a minute that what measuring in case of qubit means. So we can either perform some operation or we can either measure the qubit. These are the two operations possible with the qubit. Now suppose I perform operations, then this requirement is unitary operations. So recall that in case of a coin, we had an operation which was tossing the coin, and tossing the coin was represented by 2 cross 2 matrix. Similarly over here, the performing operation on qubit is represented by 2 cross 2 unitary matrix. Suppose A, B, C, D, some unitary matrix on this, which performs the operation on this qubit, which is a 2 cross 1 vector, a complex 2 cross 1 vector. So when I say performing operation, this is what I mean. That is, a matrix is multiplied with the vector. So with a qubit, I can either perform operation or I can measure the qubit. So performing operation requires the matrix to be unitary. That's a constraint of quantum computing. And we can perform the operation as shown. That's a simple matrix vector multiplication. And next, and the output is what the state of the qubit will be after performing that operation. So it will be what? That is C. It will be alpha A plus beta B and alpha C plus beta D. So this is the state of the qubit after performing this operation. Or we can either measure the qubit. Suppose this is what the state of the qubit was. That is alpha beta as shown over here. Right. And suppose I measure sorry for this. And suppose I measure the qubit. Suppose this was the state of qubit, and suppose I measure the qubit. So what will happen in case of measuring the qubit? So upon measurement, it will either collapse to computational basis. Now what do I mean by computational basis? Is state 0 or state 1. So upon measurement, it will either collapse to state 0 or state 1. Now what is the probability that it will collapse to state 0, or probably, I mean, can we say beforehand that it will collapse to state 0 or state 1? The answer is we cannot say. We can just give out the probabilities that it will collapse to. The probability of collapsing, the probability of state of this qubit collapsing to state 0 is given by the mod of alpha squared. That is because alpha is complex number, the modulus of the complex number squared is what the probability of getting state 0 is. And similarly, the probability of getting state 1 is what? Because the law of probability says that the probabilities must be conserved, that the sum of probabilities must be equal to 1. So the probability of getting state 1 is 1 minus mod alpha squared, or from the equation it's beta, so it's mod beta squared. That is, probability of getting the classical state is the modulus of the corresponding coefficient squared. That's what the probability of getting that state means. And clearly, because because some of the probabilities must be equal to 1, so mod alpha squared plus mod beta squared must be equal to 1. So now let's see in a more general. So this formulation is done in a more general setting over here. So let's now move on to the next part. So let us see some of the notable applications of this quantum computing, some of the good algorithms, some of the famous algorithms. So we'll start with Grover's algorithm. Grover's algorithm is basically used for unstructured search. Now, what do I mean by unstructured search? I mean, you might have heard about unstructured search in if you're a computer science student. You might have heard about something known as linear search algorithm. So that's what we are going to see. So suppose we are given 2 power n such state. I mean, x belongs to 0, 1 power n, which means that x is something like 0, 0, 0 n times, or something something 0, 0, 0, 1, 0, 0, 0, some which is n qubits, n or n qubits represented as this. So x is this kind of state, and we have a function which maps the input to either 0 or 1. So I have a function which takes some input and maps it to either state 0 or state 1. Suppose 0, 0, 0 is mapped to 0, 0, 0, 0, 0, 1 is mapped to this, 0, 0, 0, 0, 0 is mapped again to 0, and so on and so forth. I have this kind of function. Now f of x is equal to 1 is said to be marked state. That is the search element that we are looking for. That's the element we are looking for. So we want to an algorithm such that if f of x is equal to 1, return that element, or if there is no f of x equal to 1, then conclude that no f of x, that no such x exists, and f of x is equal to 0 for all x. Now, if you remember, if you recall that in case of the classical, in case of classical computing, the algorithm for doing this, which is unstructured, that is now what do I mean by unstructured over here is that there is no structure in the data. That is, the data is not in ascending or descending order where we can use binary search and so on, but over here the data is unstructured. There is no structure to the data, and we are looking for a element, searching for an element which is marked 1, or which is element that what we want. Now in case of the classical algorithm over here, we often use is linear search, and which is time complexity of O of n. Even if you use probabilistic algorithms over here, for constant error, the time complexity will still be omega of n. So it cannot perform better than O of n in case of classical computing setting, or classical algorithms cannot perform better than O of n. But let us talk about the optimal solution, which is Grover's algorithm. Grover's algorithm does the same thing in O of root of n. So you see there is a quadratic speed up over here. Now it might not seem a very good speed up because it's just quadratic speed up, but mathematically it has been shown that this quadratic speed up is actually the best we can get in case of a unstructured search algorithm. So the best algorithm, the best possible speed up, best possible time complexity that we can get for unstructured search is root n, O of root n, and that's what the Grover's algorithm achieves. So it's an optimal solution. The Grover's algorithm, the Grover's algorithm is the optimal solution to this unstructured search problem. So let us understand what does this is what I will give just a rough idea on what Grover's algorithm actually does. So consider that these are the alphas are the amplitudes of the function for all i's. So I equal to 0 to 1, so on and so forth. Alpha I is the corresponding amplitude. And so what we do is we start with an initial superposition state. That is, we create an equal superposition states of all the input states. Recall that these are the input states, and we create a superposition of all the equal superposition of these input states, and then we pass it. And this can be and the superposition state can be done in a, this is over one step. This can be done in just one go on a quantum computer, but not on a classical computer. If you want to perform the same thing on a classical computer, it will take O of n directly, because creating superposition for each and every entry takes O of n. But in a quantum computer, this takes O of 1. Then what we do is we flip the, using something known as oracle, we flip the corresponding entry, ith entry, or the mark state. We flip the mark state, the amplitude of the mark state, and then we increment the amplitude of the mark state using some algorithms and some gates and all, some operations. We flip the mark state and increase the amplitude, and because the sum of the amplitudes must be equal to 1, that is the sum of them, because the probabilities must equate to 1, the sum of the amplitudes must also be equal to 1, square of the amplitudes in other words must be equal to 1. If the mark state amplitude increases, then the amplitudes of the other states must decrease, and that's what you are seeing over here. And performing this again and again, we get the amplitude of mark state to be very high. And upon measuring that, upon doing a measurement operation, because the amplitude of the mark state is high, the modulus of squared of the mark state will be high, so it's a higher probability of getting the mark state, and this is how we can search for that mark state. So this is the basic idea, a rough idea behind how Grover's algorithm works, and why is it bad, why is it good to have a Grover's algorithm. Because because of the optimal solution, that is the O of root n, although its quadratic speed up, it's not much, but the solution O of root n is optimal. That's the best time complexity that we can get in case of unstructured search. And this is how I explain the working of Grover's algorithm. Let us move on to Shor's algorithm. Now, RSA encryption, if in cryptography, which some of you might have heard or not, I don't know, but yeah, RSA encryption uses in the back uses something known as factoring of composite numbers. So, given a positive integer, say n greater than equal to 2, I am required to know its prime factorization and output, the prime factor, the output of the Shor's algorithm to be prime factorization. So, this is what I am looking for, the prime factorization of a given number, a positive integer n. So in case of classical algorithms, something known as using number field C by Aristothensis, we get the time constant to be exponential in the number of bits. N is the number of n is the the integer, so log n will be the number of bits that the integer has. So exponential is the number of bits. So the classical algorithm, the best known classical algorithm, asymptotically gives a complexity of O of e power 1.9 something. So it's exponential in time complexity. On the other hand, the Shor's algorithm gives a polynomial time complexity. If you see, there is an exponential speed up. In quantum computing, the quantum algorithm, which is Shor's algorithm, gives the exponential speed up. That's O of log n squared log of log n. Whereas the classical algorithm, the best known classical algorithm, is still exponential. So over here we get an exponential speed up. The HHL algorithm. Now, solving linear system of equations is one of the most important aspects in any scientific computing, right? Because solving linear system of equations arises in many solving differential equations and many real world problems, solving many PDEs and so on and so forth. So, an HHL algorithm is the quantum equivalent, saying the same thing in HHL algorithm is what was developed by three people, Haro, Hasidim, and Lloyd, who developed this algorithm named after them. So, and they were the ones to discover this algorithm to solve the system of equations, which is called quantum linear system problem. So, given a linear system of equations, we are supposed to find the x, that is the solution of that system of equations, such that a cat x equal to b. There are classical algorithms like Gaussian elimination, value factorization, QR, which have time complexity of O of n cube. Then there is steepest descent, which is the iterative method, which is O of S n kappa log of 1 by epsilon. Epsilon is the error between the actual solution and the computed solution. S is the sparsity, and so on and so forth. If you have sparse matrix, then you can use this as an advantage, and so on and so forth. In case of quantum algorithm, the speed up is exponential. You see, it depends on n. And over here, it depends on poly of n, where n is equal to 2 power n. So it's logarithmic, log of n, right? So it's a polynomial, it's exponential speed up in case of quantum algorithms. So although it depends on kappa square, there are certain improvements using variational amplitude, variable time amplitude amplification. We can reduce the time velocity from poly of n kappa square to over here kappa, and so on and so forth. But we can the caveat over here is we cannot get the explicit entries of ktex. Like if you are interested in finding each and every component of ktex, you cannot get that because that requires exponential number of measurements to determine ktex exactly. But we can use this as a subroutine in some algorithm. Some bigger algorithm can use this as a subroutine to leverage it to you. We can leverage this algorithm for some function of that operator. You can use this as so. So okay, now we'll talk about classical versus quantum computing pros and cons. So there is a theorem which says that a quantum circuit of size s acting on n qubits can be simulated by a classical circuit of size O of s n squared 2 power n. So if you see there is an 2 power n over here. So it's exponential in the qubits, exponential in number of qubits. Qubits. So if you are interested in, so then the question is, can we not simulate quantum computers on classical computers? Yeah, we do so. We do simulate quantum computers on classical computers because currently the quantum availability of quantum computers is very sparse. It's very less. So we can simulate quantum computer on a classical computer, but the time complexity, current known best time complexity required is exponential. So it's exponential in space and exponential in time, but the exponential in space could be using some methods could be reduced to polynomial, but it's still exponential in time. So simulating a quantum circuit or a quantum computer on a classical computer is basically an exponential in time cost, which is very high. But on the other hand, any classical circuit can be asymptotically efficiently implemented using a quantum circuit. This is another theorem. Yeah, so now let us talk about universal gate sets. So universal gate sets are the set of gates that can simulate any other gates. For example, in case of classical computing, if you recall, mand, which is not an and, or nor gates are universal gate sets, because using nor gates I can simulate any other classical gate that is there. Using NAND gate I can create any other classical gate that is there. Similarly, in quantum case, using C naught plus Hadamard plus T or Toffoli gate plus Hadamard, I can create any other any other gates that is there. So using these three gates or this gate set of this gate, so like in case of classical computing where there exist universal gate sets, similar in case of quantum computing there exist universal gate sets which can be using which we can create any other gate set or any other gates. So there is a Soloviev-Kitev theorem which states that all choices of, so then the question arises that which gate set is better? Is C naught plus Hadamard a better or is C naught or Toffoli plus Hadamard a better choice? So there is a theorem by Soloviev and Kitev which says that all choices are equivalent. So it doesn't matter which choice you take. We can create any other gate to any arbitrary precision using O of m polylog of 1 by epsilon gates. This is a theorem which states that. So any choice of universal gate set is equivalent in case of quantum computing. Yeah. So one more thing that the people might be concerned about over here is that the probability of, so because the quantum algorithms are inherently probabilistic, because qubit upon measurement gives a probabilistic result, a distribution, right? It's not a deterministic output, so it's a distribution. It's a probability distribution as an output. So then the question is that what is the required probability? So because it's probabilistic output, we might require many more experiments or many more performance of many more passes of the quantum circuits to get the correct output or get the correct result. But that's not true. I mean, if you see, suppose the probability of getting the correct outcome or the correct answer is just greater than equal to 1 by 2 plus epsilon, where epsilon is just some small value greater than 0. Then using Chernoff bound, we can show that the probability of getting the correct answer increases exponentially, or the probability of getting wrong answer decreases exponentially. This is for a binary outcome. The outcome could be 0 or 1. So for a binary outcome, we can show that the probability of getting the correct answer increases exponentially, or the probability of getting wrong answer decreases exponentially. So error gets exponentially small. So the error in computing gets exponentially small if the probability of getting the correct answer is just greater than 1 by 2, just greater than half. Okay, so now let us talk about the challenges of quantum computing. So although this might seem a good thing about quantum computing and so on, but there are certain challenges to quantum computing. For example, linear growth and Domals principle. Now this principle states that if suppose because we are implementing unitaries, which is a continuous state space, right? Because unitary, the values in unitary could vary continuously. It's a the values in unitary are complex values, and the complex values can vary continuously, right? Unlike in case of classical computing where the values will be discrete. I mean, it can be either state 0 or either state 1, but over here it's alpha cat 0 plus beta cat 1. So alpha and beta are complex numbers, and complex numbers could be varying. I mean, could be vary by very small amounts, and so it's a continuous state space. Now, because it's continuous state space, unitaries over here acting, we might not be able to implement. I mean, we can implement any unitary, but we might not be able to implement unitary exactly. So there might be some error in implementing unitaries. Suppose I want to simulate UI, which is a complex n cross n matrix, and I'm able to implement UI tilde, which is an approximation, a good approximation to that unitary. Of course, because as I said earlier, that the complex, the complex vectors over here, because we are in a continuous state space, it's we can approximate, or we can get a good approximation, but we might not be able to get an exact. I mean, it's hard to get an exact values. So over here we talk about approximations. So in quantum computing we generally talk about approximations. So suppose I have a unitary UI which I'm interested in implementing, but I'm able to implement UI tilde, which is an approximation to that unitary for all, and there are k such gates. There are k such gates that I need to implement. Then the Duhamel's principle states that the error, if the error, the induced norm error in UI and UI tilde is less than equal to epsilon for all epsilons, then the overall implementation of the entire unitary, that is U1 to UK or U0 to UK, and the difference between U0 to UK and U tilde 0 to U tilde K, this is K epsilon is less than equal to K epsilon. That means the growth is linear, which is also a good thing, but there is a growth that's also a bad thing. So too many gates is not desirable. In other words, the statement says simply that too many gates is not desirable because the error grows linearly. Now let us talk. So what are we talk about in this in quantum computing setting? Whenever we talk about quantum computing or scientific computing, we neglect the errors arising due to approximation at the mathematical level, or approximation. I mean, errors due to Monte Carlo, that is probabilistic nature of measurements. We do not consider those errors, and we consider the error. Consider the errors only which arise from the approximation errors at the mathematical level, or the okay, or the errors which arise from Monte Carlo due to measurements. I mean, we do not talk about the errors which are because of the implementation errors, like not implementing the gate correctly or up to a good accuracy. We do not talk about those errors. We always assume that the gates implemented are exact, and they work perfectly. That's what we always assume in case, and that's what the meaning of fault tolerant computation is, that there are no faults in the computing aspect. The only faults or only errors that arise are due to the approximation that we do at mathematical level, or because of the probabilistic measurement, because of the probabilistic nature of measurements, the Monte Carlo errors that arise due to probabilistic nature of measurements. Now, one of the requirements of quantum computing is also reversible computation, which is a necessity of quantum computing. Now, what do I mean by reversible computation? So reversible computation means something like, because we talk about unitary matrices, as I said, the evolution of qubits is unitary. That is, you have a qubit, you perform a unitary operation on it to get another state of the qubit, some state of qubit. Right? You change qubit from one state to other state using some unitary operations. Now, because the operation is unitary, we can perform a U dagger operation on this state to get back to the original state, right? Or U, because U dagger is same as U inverse. So if I have, say, U cat phi is equal to cat psi, then I can pre-multiply by U dagger on both sides, and U dagger we knew is equal to identity, so we can recover cat phi again, right? So if I have cat psi, and if I know the operation performed with U, then if I multiply U dagger with that cat psi, I'll get cat phi back. So that's what reversibility means. That's what reversible computation means. That is, if you are in one state, you perform a unitary operation to get another state. You can perform a U dagger state inverse unitary operation to get to the original state back. And this is not something of a choice, but it's a necessity, because all the operations to be performed are unitary. So now if you recall in classical computing, this is not any requirement. There is no requirement of the functions to be unitary. I mean, we can find any function which is not unitary and we can still solve the problem classically. But quantum computing requires the problems or the functions to be implemented to be unitaries. And so the thing is that we can implement any non so we can also convert any non-reversible function to the reversible function using this method over here. So yeah, so if you see, let me clear the screen. Okay, so so this okay. So now we talk about how do we perform this reversible operation. So this is a diagram showing that how we can perform a function, a non-reversible function, reversibly. Now I will not go into details of this because it's too difficult to too much time to understand this, but because of time constraints. But yeah, this is what is interesting in case of a is useful in case of a is a necessity in case of a quantum computing. Okay, no cloning theorem. Now the thing is that you can suppose in classical computers you must have done copying, like you copy a file from one place to another, you copy a file from your laptop to your pen drive and then to someone else's computer and so on and so forth. So that copying is allowed in case of a classical computer, but the same thing is not allowed in case of a quantum computer. Quantum computer does not allow copying or cloning. So if you're given an unknown quantum state, I cannot copy that quantum state to some another quantum state on same quantum state. Both are unknown in that case. If the quantum state is known, then I can of course recreate that state. So that's not cloning. If a quantum state is unknown, I cannot copy that state or I cannot clone that state to some other quantum state that I have. So that's no cloning theorem. Then distinguishability of non-orthogonal states. So suppose recall that we do a measurement at the end. So in general, of after performing algorithm, we generally perform a measurement at the end. Now if you recall, the measurement is so if you recall, measurement collapses the quantum state to one of the classical states. Now the requirement, another requirement of so at the end, so at the output of the quantum algorithm, I need my states to be orthogonal. If they are not orthogonal, then there is no way to perform a measurement which can collapse it to the correct answer. In other words, what I mean is that there is no measurement which can distinguish non-orthogonal states. So if I want my answer to be correct, or at the end of the algorithm, if I want a better answer, correct answer, then I want to design an algorithm such that the output of the answer is orthogonal states. That the state of the or the outcome of the algorithm must or is preferred to be result in orthogonal states, so that I can create a measurement which can distinguish those orthogonal states better, and I can get the correct outcome. Non-orthogonal states, as I said, cannot be distinguished perfectly. There is no measurement which can distinguish non-orthogonal states. So some other challenges are quantum query complexity. So if you recall, we had a UF, that is a function, quantum implementation of a classical function f. So query complexity is the number of gates or the complexity required for implementing the quantum function UF. The total gate complexity is defined as the quantum query complexity of the circuit plus the algorithmic complexity. Now query complexity is supposed or is preferred to be greater than the algorithmic complexity. So the total gate complexity is approximately equal to query complexity. Now the thing to note over here is that the algorithmic complexity should be less than the query complexity. Why is it so? Because if the algorithmic complexity itself dominates the circuit, then it's better to perform that same operation on a classical computer than on a quantum computer, right? So the query complexity should dominate the entire algorithmic complexity, and the query complexity should be, that's why we say when we talk about total gate complexity, it is approximately equal to the query complexity. Yeah, the circuits that we design should be depth efficient. Now, what do I mean by making them depth efficient? So, because of fidelity, that is, because of the current quantum algorithms, the gates are not implemented correctly, and there is less coherence as the time proceeds because the loss of coherence in between multiple qubits. We prefer to have the depth of the circuit to be less. And what do I mean by depth? Depth is basically the when you talk about a quantum circuit, the number of gates applied on a qubit is what we call depth of the circuit. I mean, if the number of gates is very high, then the depth is very high. So depth is approximately equal to the number of gates that we apply on a qubit, on a single qubit. So the depth of the circuit should be as much less as possible. That is, the circuit should not be very long, because it's preferred to have a less circuit depth circuit and to run it multiple times than to have a higher depth circuit and to run it single time. That's preferred. So circuit depth, as I said, is the maximum number of gates. Circuit depth, as I said, is the maximum number of gates on any path from input to output, which is equivalent of saying classical wall clock time. So if you have more number of gates, more the time it will take. So it's equivalent to saying classical walk time. So the number of gates on any path from input to output is an indicator of the time taken by the circuit in some way, in some classical equivalent sense. That's how we define the circuit depth. So we want similar, as we want the classical time complexity to be less and as much less as possible, we want the circuit depth to be as much less as possible, so that it will take lesser time. And also because of the coherence problem, that is, the qubits become decoherent as they move through the quantum circuit. So yeah, that's what coherence time is. Coherence time is quantum states can be preserved only for a short amount of time. So as I said, the quantum states, the qubits, can be only preserved for a short amount of time because they get decoherent because of the noise and all. In nature they get decoherent. So we want so there is a certain coherence time to those qubits. So we want the circuit depth to be less than the coherence time, because if circuit depth is more than the coherence time, then the output will be garbage, because the output won't make any sense, because all the qubits are decoherent by the time they reach the output. So we want the circuit depth to be less than the coherence time, and circuit depth is equivalent of talking about classical wall clock time, which is the time that is required for a qubit to reach from start to the end. The number of gates in the path of the qubit is what an indicator of the classical wall clock time, or the circuit depth. So we want the circuit depth to be less than the coherence time in order to get meaningful solutions. Yeah. So yeah, one more statement is that we generally prefer to free up the ancillary registers whenever possible. So in order to perform say non-reversible classical function on a quantum computer, will require extra bits, which are called ancilla bits, in order to perform those operations, which are done in auxiliary registers for implementing the unitary. So it's preferred, or it's better to free up the ancillary registers once they are used by performing the uncomputation step. So yeah, and whenever we talk about analysis of in quantum computing, we always talk about ancillary bits. How many ancillary bits are required? How many ancillary bits are used in the algorithm? So it's preferred to free up the ancillary registers in order to have to minimize the use of ancillary bits. So the lesser number of bits, the better the algorithm. The lesser the circuit depth, the better the algorithm. So these are some aspects of quantum computing which are to be noted, and which are challenges in the current quantum computing algorithms. So yeah, that's all for today. Thank you.